Next, we're going to look at how to connect these components together and actually get them to change state in a controlled way. And as a warm-up, we're going to look at the program counter, which is, as you'll see, is kind of a mini computer. So the idea is what we're doing is designing a digital sequential circuit in such a way that we have precise control over feedback cycles. And so we've already described our interface. We have input buses, output buses, and control signals, and what we expect components to do. Then the next step is to figure out the connections that we need between components, one component to another. And then we have to establish the sequence in which the control wires, like the right wire, become one. Those are the steps. And we're going to, as a warm-up, just look at the Toy 8 program counter, or the PC. It's a little digital sequential circuit. There's a couple of things that we need. The first thing is it needs to increment. So we need a circuit to increment the PC. That's relatively easy. And then the second thing is we have to consider what happens when we have multiple buses connecting to the same circuit. And that's also relatively easy, but it takes a little bit more thought. So let's look at the incrementer. Well, this is actually just an exercise in designing a combinational circuit. We need to design a circuit to compute x plus 1. We could actually use a full adder and just feed in 1 and x. But it's worthwhile to just start with a slightly circuit built for this purpose, just as an exercise in designing a circuit. So what we'll do is we'll just start with the adder idea, but we'll just forget about the y inputs and then set the carry in to 1. So it's like you have a number x and you're adding it to 0 with a carry in of 1. Then these are our tables. So over on the left we have the carry bits, we have x, and then we have to figure out how to compute the next sum bit and the next carry bit. So carry bit now is just 2 bits, the carry in x, and then the only time that we have to carry a 1 out is when those are both 1. Well, that's nothing more than the AND function as shown in the truth table at the left. In the sum bit, we have our 2 bits. If they're both 0, the result is 0. If one is 0 and the other 1, the result is 1. If they're both 1, the result is 0 with a carry the 1. And now if we look at that truth table, that's just XOR. And so we're going to do the same thing as with an adder, except with an AND and XOR rather than the majority and the odd parity. And so that's our incrementer. Just like the adder with a bus X at the top, and XOR with the carries carried through the same way as we did in the adder. And then the value x plus 1 is always available at the bottom. It's a nice exercise in doing a combinational circuit. So that's our incrementer. That's going to be a component in the PC. Now the other problem that we have to consider is what about having multiple bus connections in components. So if we have component outputs that need to go to multiple other components, well, there's no problem with that. We just use T connections. Just a wire comes through and we just connect to that wire. It's got the same value. The values on both of the buses are the same, and we use that like the register has to connect both to the ALU, because sometimes the register is one of the operands of an arithmetic operation, and it also has to connect to the memory for a store operation. But the other way, if the inputs come from multiple other components, that's a problem. So for example, the ALU has to connect to the register because the output of an arithmetic operation might go to the register. Memory has to connect to it for a load. Instruction register has to connect to it for a load address. But how do we do that connection? The values on those buses are going to be generally different. So how do we connect it? So what we need is a selector switch for buses. It's a bus mux. And it's actually easy, but it's worth taking the time to think about this concept because it really is a key thing in the design of a digital circuit. We're going to use a one-hot M-way bus mux. And all it is M copies of the one-hot bus mux that we did the last time. So our interface is we have a bunch of input buses. In this case, we have 3 input buses. And for each input bus, we have a selection line, and we have 1 output bus. And again, we're going to have the precondition that at most one of the selection lines is 1. And the output bus is going to have the same value as the selected input bus lines. And so in this example, there's 3 different values going into the 3-way bus mux at the top right. They all have different values, but in this case, select 2 is 1. That's the bottom one, and those values are the one that are going to appear as the output of the bus mux, which we use as input to the next circuit. And again, we take output back to input by snaking around like that just to make it clear what's the output and what's the input. To make it even more clear than the top-bottom relationship, the right-left relationship is we're going to stick to that to make it very clear where the buses are coming from and going to. That's the description of the bus mux. We actually have 2 of these. Now, again, as with all muxes that we talked about before, it's not that there's a direct connection from the input to the switched output. It would be misleading to say there's an electrical connection. It's just that the signal's the same. Whatever the 1-0 pattern on the input is the same as the 1-0 pattern on the output. And again, this is very easy to implement. It's just for each bit, we just do our one-hot mux for each bit. Extremely simple, just ANDing the selection line with the corresponding bit line. Only one of those selection lines is 1, so then only one, and then there's vertical OR gates collecting the results, as always. So only one of the inputs to the OR gate is 1, so it does the job as we've done in several other circuits. So we're going to need this right away to implement the PC to select among 2 different inputs to the PC. All right, so what's the interface for the PC? So it holds an address. It's got an input bus. We might have to load the PC from somewhere else in the case of a branch instruction. Branch instruction, we load it from the address bits of the instruction register. And then it's got an output bus that's always available that's going to be connected to the memory to get the instruction out of the memory. So our control wires are, though, that there's different things we might want to do. So one thing is we might just want to increment it when it's time to change its value. The other thing is we might want to load from the input bus when it's time to change its value. And then we have a write signal, whichever is up, increment or load, that write control line will cause the value to actually change. And then it's a register. The current value is always available on the input bus. So clearly it's going to have a 4-bit register inside. It's going to have an incrementer inside. And now we have to consider the connections among those 2 components that we need in order to implement this behavior. So clearly we need to go from the input bus to the register. There has to be a way to load the register from the input bus. We also have to go from the incrementer to the register. Once x plus 1 is known, that's got to go into the register at some point. Then from the register to the incrementer, that's the number to increment. And then from the register to the output bus, that's how we make output available. But the thing is that once we determine these connections, that tells us that we're going to need a bus mux, because we have two connections to the PC register input, and those might be different at different times. Of course they'll be different. The value of the PC plus 1 is going to be different than the address bits of the instruction register. So that tells us we need not just those components, but we also need a bus mux. The actual picture is this. So we've got the PC register, we know what that is. We've got the incrementer at the top, we know what that is, and we've got the bus mux in the middle, and we know what that is. And then we can check the connections one at a time. The input bus is one of the connections to the bus mux. The incrementer, so the bottom, that's the output of the incrementer, goes into the top increment of the bus mux. Those two match up with the increment and load selection signals for the bus mux. So when increment is high, it's the incrementer that goes to the output. When load is high, it's the input bus that goes to the output. The output of the bus mux gives the input to the PC register. PC register loops around to the incrementer and also goes to the output bus. So that's the complete set of bus connections and control lines for the program counter. With these connections and these circuits, it's going to have the proper behavior. Really, it supports two different control signal sequences. So that is, if load comes up and then there's a write pulse, what'll happen is it'll set it'll take what the value available on the input bus and store it into the PC register. That's what happens when we have a branch instruction. And that value is available on the output bus. On the other hand, if increment comes up and then write, then it results in adding 1 to the value. The output of the incrementer goes through the bus mux into the PC, and the write pulse happens, then the values in the PC register change. And in this case, we have a long feedback loop back into the PC. And that's a very important note. This is the reason we have the short write pulse. We want to get those values to change, but we don't want to, if we didn't have the short write pulse blocking, the thing would just keep incrementing. It only has the chance to change values during that very short pulse that is just enough to get a flip-flop to flip. So those are the two states, and that's exactly what we want to support in our program counter. In order to get it to do what we want it to do, we have to give it those control signal sequences. If we do something else, if we leave right up for a long time, we're going to get some unpredictable behavior. So we have to arrange to do that. Now, the art and science of designing sequences of pulses like this is really the heart of processor design. And now we'll look at these same principles in the context of the whole processor.